One of the issues right now with the transformer is that the architecture of the transformer is not scalable. So let's say I take a small GPT-2 that has 12 layers and has a 768 dimensionality. I cannot just finish training my small GPT-2 and then continue and train a larger model, because the larger model, not only is it trained on more data, but the architecture is fundamentally different than the GPT-2 small. We're going from 12 layers to 24, and we want the model to have a richer representation of the token. So we're going from 768 to 1024. So because I'm changing the architecture, the model needs to be retrained from scratch, and that is unfortunate because I have lost the cost used to train this one. And overall, it is just an inefficient use of compute resources. So what if we can have a new architecture of the transformer that is actually scalable, where I can start with this one and organically upgrade to this one without losing any of the training cost? This is what this paper is about, TokenFormer, which is a new architecture that allows the transformer to be scalable. Instead of scaling in the traditional sense, in terms of adding more layers or increasing the model dimensionality, we're going to scale in the access of adding what we call token parameters. So this is what they mean here with tokenized model parameters. These are parameters. Think of them as a way to replace the way we scale a transformer. And so we're going to add more of these parameters, and in a way we're going to mimic the scaling that comes when you scale the dimensionality or the layering. Okay, so before we jump into this new architecture, let's just take a step back and understand what makes the transformer not scalable. Once we understand that, we're going to be better able to understand what this paper is about. So we have our transformer right here. You have these multi-head attention components. We have 3 of them in this encoder-decoder architecture. If we zoom in inside the multi-head attention, you'll have something like this, which it's a bunch of linear components. Okay, it gets fed the same inputs. So in this case, it's not really the Q, K, and V. It's just like your regular token. But outcomes query in this case, the key and the value in this case. Then you have your dot product attention, which for every token, it assigns how other tokens are important to it, and it recontextualizes itself based on that new exchange information. You also have multiple heads here, and then you concatenate all of that information, and you have yet another linear component right here. So zooming into one of those, and I have this figure right here. Let's say you have this token right here, which is just a vector. We pass it through 3 MLPs, and the same token is going to be converted into different sets. So it's going to be converted into query right here, into the key, and into the value. Of course, each one of these have their own function. The query, it's all about what am I looking for. The key is this is what I'm representing, and then the value is the actual meaning of the token. One of the ways that a transformer is scaled is by how wide the dimensionality of the vector, or the richness of what you can represent in a vector, and that needs to scale. And this cannot scale with the fact that these MLPs, they have fixed amount of parameters. So these are fixed, and this is what limits the scalability of the transformer. And if you go here, it says that the transformer are great, but one of the problems that prevents the scaling comes from the fact that they have a fixed number of parameters within linear projections. And whenever we actually want to change this dimension, it actually requires a complete retraining from scratch. So to overcome this problem, they introduce the TokenFormer. It's a scalable architecture that leverages the intention mechanism. We're going to talk about that. not only for computation among the input tokens, okay, which is currently the case. We have attention for input tokens, but we also have an interaction, and that's new, between the token and the model parameters. Okay, by treating model parameters as tokens, we replace all the linear projections in the transformer with our token parameter attention layer. And so here they say we're going to increment those new key value parameter pairs, or those token parameters. They started to train a model with 124 million parameters, and they scale it to 1.4 billion parameters just by scaling. And they achieve comparable results to transformers that were trained from scratch. So this graph right here shows that what's in blue is what has been trained from scratch. So these are, for example, this is the biggest model trained from scratch. But here they have incrementally scaled TokenFormer, and they got pretty much the same thing. So think of perplexity as like intelligence, or the inverse of that. So the lower perplexity, the bigger the intelligence, and they were able to get pretty much comparable results with less training cost. Now let's jump into the meat of the paper, which is the actual architecture itself. So the most important idea here in this new architecture, it's all about tokenized models. So here the MLP, okay, in a way it's sort of like the death of the MLP, because they're going to be replacing the MLP right here. They're going to be replacing the MLP with this new P attention layer. So the input that comes into the MLP and the fixed parameters here, the whatever gets stored and in these parameters, and the processing that happens in these parameters, they're actually going to be converted into tokens. And those tokens comes in two sets, the key tokens and the value tokens. And in those tokens, they're going to represent discretized units of whatever the MLP used to do. So they're going to be kind of discretized units of storage, discretized units of processing, and discretized units of model knowledge. And the only way to process that is in this attention layer. The fact that these little tokens here are discretized, and the fact that they can be variable, right? So more tokens means we can scale the model. The only way for that to coexist is in an attention mechanism, where you do a cross attention between the tokens and the key and the value param tokens. And this is what they mean by tokenized models. This attention mechanism right here is going to learn which key value pair tokens are going to be the most relevant to the input. So the fact that this can be variable length, this is what makes TokenFormer scalable, because we have taken the fixedness of the MLP and all of the other stuff the MLP used to do, and now we can, in a way, do the same thing in a variable sense by discretizing these things. And so now we can add as many of those tokens as we want. So for example, let's say I've trained a smaller transformer with these old tokens right here, and then I finish the training, and then I want to scale to a bigger model. I can just append new tokens and then continue from scratch. The fire here, the fire symbol, means that we can still propagate through the old tokens as well to further fine tune them. And so the way these tokens, these variable length tokens, interact with the input is through a cross attention. So in this paper, there's a lot of MLPs in a transformer, right? So there is these MLPs, there's three here. There's the output MLP, and then you have the feed forward here. And this is what they show in this section right here, is that every one of those MLPs, those 5 MLPs are going to be replaced by these P attention layers right here. So the MLP to generate the query, and the MLP to generate the key, the MLP to generate the value, as well as the MLP that processes the output of the token to token attention, and the feed forward neural network are all going to be replaced by this P attention component. So let's mention one more thing about this new P attention layer. It says here that the P attention, it uses a set of vulnerable tokens to represent model parameter and lets the input tokens attend to them. So the fact that there's a P attention in different spots right here, the P attention is going to carry out different functions. So here it carries out the function of generating queues, the queries. Here it carries out the function generating keys. Here is for the value. Here the function would be how to process the concatenation of all the heads after they've done their token-to-token intercommunication attention. And here it performs the fully connected MLP. So for the token to update themselves. And so the funny thing it's that this architecture works for all of these functions while keeping the feature dimension constant and leaving the rest of the computation unaffected, which means that my sort of underlying architecture is fixed, but the variableness right here, that pool has a variable length and allows me to scale within that. And that scaling within that space right here of these tokenized units mimics the scalability that happens in the traditional transformer along the number of layers and along the size of the vectors or the dimensionality.